All right, everyone. Well, welcome to Unit 4. Our introduction today is going to be on formative, as you can see. and what we're going to start with is a review of valence electrons. So you may remember at the beginning of Unit 3, we talked a little bit about dot diagrams and about the difference between ionic and covalent bonding. So in this unit, we are strictly looking at covalent bonding and molecular compounds. So these are atoms that are only going to share their valence electrons. So just a reminder that all neutral atoms are going to gain, lose, or share electrons to end up with that full valence shell, the full valence shell being the same number of electrons as the noble gas group. For most atoms, that ends up being 8 electrons. You'll notice that most noble gases have 8 electrons. But for some elements like hydrogen, when hydrogen gains 1 electron, it's going to have the same configuration as helium, for example. So when it shares a pair, it will have the same configuration as helium, rather. Okay, and also just a reminder that it's only the valence electrons that are involved in chemical bonding. So, if we think about how many valence electrons are in atoms on the periodic table, group 1 has 1 valence electron, and so you see 1 dot represented there. In group 2, those elements will have 2 valence electrons, so you'll notice 2 dots there. Groups 3 through 12 are the transition metals, so we're going to skip over those. We start with boron in group 13. These elements will have 3 valence electrons, as represented by the 3 dots here. And then we have group 14, 15, 16, 17, and 18. And again, going across from left to right, skipping the transition metals, we see 1, 2, 3, 4, 5, 6, 7, and 8 valence electrons represented here. And so these are the electrons that are involved in bonding. Okay, so when we draw Lewis structures for molecular substances, remember that this is going to be at least 2 atoms bonded together. And so only nonmetal atoms, remember, okay, because those are the atoms that have relatively high electronegativity, so that neither atom wants to give up their electrons. Okay, and so if we take a look at this image of the simplest molecule that we could possibly draw, which would be H2, you notice that each hydrogen has 1 valence electron. Okay, so we've drawn that 1 valence electron on each of those. And so if those 2 hydrogen atoms share that pair of electrons, then that would be a single covalent bond. And you'll notice we draw that single covalent bond as a single line, okay? So that single line represents a shared pair of electrons, or what we call a single covalent bond, okay? And so this is, again, remember that hydrogen, now that it has 2 electrons, so now that each hydrogen has 2 electrons around it, okay, they both have satisfied kind of that noble gas or full valence shell that it wants. Okay, if we take a look at a more complex molecule, really not more complex, but just with more valence electrons, so 2 fluorines, so F2, which would be elemental fluorine. So we're looking at 2 fluorine atoms, each with 7 valence electrons. Okay, but you'll notice that each one has 1 unpaired electron then, okay? And so it's these 2 electrons that are going to end up being shared in the center, okay? And so that's what we call our bonding pair of electrons. You'll notice that each fluorine also has 6 what we call unshared electrons, or lone pairs, okay? So there's 3 lone pairs on each and 1 bonding pair on each. And so you'll notice that we again replace that shared pair of electrons with a single line representing the covalent bond. Okay, and if we think about each fluorine, so the fluorine on the left would have 8 electrons, and the fluorine on the right then would also have 8 electrons, because those 2 electrons in the middle would be assigned to both atoms. Okay, and so this is just an example with a few more valence electrons, and then making a distinction between the lone pairs and the bonding pairs of electrons in a Lewis structure. Okay, so for compounds that contain more than 2 atoms, how are we going to decide how those 3 atoms are arranged? So the first thing we're going to need to do is we're going to decide which atom's going to go in the center of the Lewis structure. We call this the central atom. And in general, when we write chemical formulas, the least electronegative atom comes first in the formula. Okay, there are a few exceptions to that. H2O is not an exception to that. So if I write the Lewis structure for, or if I write the formula H2O, okay, we'll talk about electronegativity another time, but hydrogen is less electronegative than oxygen, okay? So typically the less electronegative atom is going to go in the center. The only exception to that is hydrogen. When hydrogen is written first, it can never be the central atom. And so in the case of something like H2O, we've put oxygen in the center. Okay, so you'll notice that we have H2O with its 6 valence electrons in the center. We have a hydrogen with 1 valence electron and a hydrogen with 1 valence electron. And so you may notice that, so for example, these 2 electrons here can join together to form that shared pair, that covalent bond that we talked about. Okay, and so we see that here. Okay, and you'll notice that now we have, again, the 2 lines representing the shared pairs of electrons in between. So again, this is a covalent bond. So each of these represents a covalent bond or a shared pair of electrons. And then we see 2 lone pairs, or 4 electrons, on the central atom of oxygen in this case. Okay, so now that we have kind of talked a little bit about sort of the general idea of sharing electrons and what a covalent bond is, let's review some rules that we're going to use for drawing Lewis structures. Okay, so first we're going to count the number of valence electrons for each element. So if I have a compound like H2O, each hydrogen has 1 valence electron, okay, and then oxygen would have 6 valence electrons for a total of 8 valence electrons, for example. Okay, next we're going to assign the central atom. So in the case of water, that was oxygen because hydrogen can never be in the center. So you'll notice we say never hydrogen, and always if carbon is present, carbon will always be the central atom. Okay, and typically it's going to be the least electronegative atom, and we usually write formulas so that the least electronegative atom comes first. So that generally makes it relatively easy to determine which one is the central atom. All right. Okay, so once we kind of assign the central atom, then we're going to arrange the remaining atoms around the central atom. As we do that, we're going to go ahead and form a single bond. So if I'm thinking about oxygen and hydrogen, for example, I'm going to go ahead and put my oxygen with my 2 hydrogens there. And so remember that each of those lines represents a shared pair of electrons. And so I've used 4 electrons of the 8 that I have. Again, I have 8 total valence electrons, okay, making bonds between oxygen and hydrogen. Now, hydrogen can never have more than 1 bond. So once we form a bond to hydrogen, it is done. It can't take any more electrons. Okay, but notice that I still have 4 electrons remaining. Okay, so this is 2 electrons. This is 2 electrons. Okay, and I still have, so -4 for bonding means that I still have 4 left over. Okay, and so we're going to put the remaining electrons as lone pairs on whatever atom still needs electrons. So we just said that hydrogen doesn't need more. So oxygen, though, does need 4 more electrons in order to make sure that it has its octet or satisfies its valence shell of 8. Okay, and so once I do that, I add those 2 lone pairs. Okay, I am going to satisfy the octet for oxygen. Hydrogen was already satisfied when it has its bond. Okay, so that's the general rule, or those are the general rules that we're going to use for drawing Lewis structures. Now, there are cases where we might have not enough electrons, for example. So as we add the remaining electrons as lone pairs, we realize that we've run out before we've added all the lone pairs we need. When that happens, we're going to form double or triple bonds, and so we will represent those with double lines or triple lines in between the atoms, and each line still represents a pair of electrons. Okay, if we have too many electrons, meaning that we've satisfied all of the octets and we still have more electrons to distribute, then we're going to place those extra lone pairs on the central atom, and we'll talk about some exceptions to the octet rule here in a minute. Okay, the last thing you want to do after you think that you have come up with a correct Lewis structure is you want to make sure that you have satisfied the octet for everything and that you have used the correct number of electrons. So if I go back and look at my Lewis structure for water, I see that I've used 2, 4, 6, 8 electrons, so I've used the correct number of electrons. Okay, and I see that hydrogen has its sort of octet satisfied. It only needs 2. Okay, both hydrogens are both satisfied. And I see that the oxygen in the middle is also satisfied with 8. And so this is a valid Lewis structure that satisfies the octet rule for all of the atoms. Okay. Now, I mentioned that if we have extra pairs, sometimes we want to place those on the central atom. Okay, and so there are some exceptions to the octet rule. First are those atoms that can have incomplete octets, meaning less than 8, and so hydrogen we'll consider that an exception because it has less than 8. Beryllium is an atom that can form covalent-like bonds. We really won't look at many examples with this, with only 4 electrons, so beryllium has 2 bonds. And then boron can form compounds where it only has 6 electrons around it instead of 8. And so that is also an exception. The other exception, which is probably the most common, is those atoms that can have what we call expanded octets. So expanded meaning more than 8. Okay, and this is true for all of the nonmetals in period 3, which is row 3 or below. In general, phosphorus is the first element that we would expect to have an expanded octet. Any nonmetal above that, with an atomic number higher than phosphorus, would be capable of having an expanded octet or more than 8. Okay, so what we're going to do now is we're going to draw Lewis structures we're going to follow the rules to draw Lewis structures for several different compounds. So we'll start with ASH3. And so if we take a look at ASH3, we see that arsenic, so let's see if we can find a periodic table here. Here's one. So let's take this. We'll move that periodic table over. All right. Perfect. All right. Wrong one. Okay. Here we go. So I see that arsenic is here in group 15, which means it has 5 valence electrons. And hydrogen over here in group 1 has 1 valence electron, but there are 3 of them. So that's going to be 3. Okay, so this is 8 valence electrons total. Okay, and so we said that hydrogen can never be in the center. So we're going to start by putting arsenic in the center. And we're going to go ahead and put the 3 hydrogens around the arsenic here. Okay, so we're going to draw a single line. Remember, each one of those lines represents a single covalent bond, or 2 electrons. And so once I do that, I'm going to kind of tally up my electrons here. And so I've used 6 electrons for bonding, which means I have 2 left over. Okay, so that's how many electrons I have in order to satisfy octets. Remember that hydrogen is satisfied with just that bond that it has. And so the only atom that still needs electrons is arsenic. So we're going to put those extra 2 electrons on arsenic. And then we're going to go back and double check our Lewis structure here. So we've used 2, 4, 6, 8 electrons, which is the number of valence electrons that I had. The arsenic, which is my central atom, has 8 electrons. Each hydrogen has 2 electrons, and so each hydrogen is also satisfied. And so that is the Lewis structure for arsenic trihydride. All right, moving on to SEF4. All right, so I see that selenium, or selenium, however you want to say that. Okay, so selenium is here in group 16, so that is 6 valence electrons. I'm going to abbreviate that VE. Okay, and then I see F, which is in group 17, which has 7 valence electrons, and there are 4 of them. Okay, so that's 28. So 28 and 6 is going to give me 34 valence electrons that I need. Okay, so we'll start with selenium in the center again. Again, that first atom in the formula is typically going to be our central atom. This is no different, okay? So out of my 34 valence electrons, I formed 4 bonds, and so I've used 8 valence electrons, which means I have 26 electrons remaining, okay? So I'm going to go ahead and place those as lone pairs. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And so I've placed electrons, lone pairs, around each fluorine in order to get to 8 electrons around each. So again, here's 8, 8, 8, and 8. And then around the center, the selenium also has 8. Okay, but I still have 2 electrons left over. If you go back and recount everything we've added here, there's 8 electrons around the middle, okay, with the bonds, so 8 bonding electrons. And then we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons, plus the 8 is 32, which means I have 2 electrons that I still need to place here, okay? And so you may remember that in the rules for drawing Lewis structures, we said if there are additional electrons or too many electrons, we're going to go ahead and add that pair on the central atom. Now, you'll notice that that gives selenium 5 pairs of electrons, or 10 total, okay? And that's okay, because we said that, selenium is in period 4, so that means that since it's after period 3, that it is capable of having an expanded octet. And so that is the Lewis structure for SEF4. All right, so NH3 comes next. Okay, so you'll notice that nitrogen is in group 15, so nitrogen will have 5 valence electrons. And each hydrogen will have 1. Okay, so this is again a total of 8 valence electrons. So I'm going to put nitrogen in the center. Remember, hydrogen can never be in the center, so I don't even need to think about this. Okay, so NH3. Okay, so there's my 3 bonds. That's 6 valence electrons that I used, which means I have 2 remaining to distribute as lone pairs. The hydrogens don't need any more, and so this is going to go on nitrogen. I see that the octet is satisfied on the central atom, which is nitrogen, and I see that each hydrogen has 1 bond, which is all it can have. And so this is the Lewis structure for NH3. Okay, moving on to CBr4 now. So carbon is in group 14, and so carbon has 4 valence electrons. And bromine, which is in group 17, has 7 valence electrons. And there's 4 of them. So this is 28 and 4 is 32. And so that's the total number of valence electrons that I have to distribute. All right, so carbon's going to go in the center. We're going to put the 4 bromines around carbon, form single bonds. And so we used 8 electrons in doing that. And so that's going to leave us with 24 electrons to distribute as lone pairs. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so we've distributed 32 electrons total, 8 as bonding electrons, 24 as lone pair or lone electrons. I see that each bromine has 8 electrons around it, so it's satisfied the octet, or that full valence shell. The carbon around the center has 4 bonds, so it also has 8. And so we have satisfied the octet and met that full valence shell requirement for all of the atoms in CBr4. All right, moving on to SF6. SF6, so sulfur is going to have 6 valence electrons. Fluorine is going to have 7 valence electrons. And there's 6, okay, so there's fluorines here. So 6 times 7 is 42. And 6 valence electrons means that this is 48 valence electrons that we have, okay? All right, so sulfur, again, going to go in the center. Typically the first atom in the formula is going to go in the center. And now I have 6 fluorines, okay? So again, remember that sulfur is one of those atoms. It is in the 3rd row, 3rd period, okay? So it can have an expanded octet, okay? So 2, 4, 6, 8, 10, 12. So I've used 12 electrons for bonding. And so that means I have 36 electrons remaining that I can place as lone pairs. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28, 30, 32. oops, sorry, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Okay, so there's my 36 electrons. Sorry about that. Okay, so we used 12 around the middle, 36 around as lone pairs. Okay, so we see each fluorine has 8. Okay, so if I kind of circle the 6 dots and the line there, that represents 8 electrons. And so each fluorine has 8 electrons. Okay, the sulfur around the middle does have an expanded octet, but again, it is in the third row, so that's fine. Any nonmetal in the third row or below, it's meaning 3, 4, 5, and so on, can have an expanded octet. So we are fine with sulfur having 6 pairs of electrons. And so that is the structure for SF6. All right, so let's take a look at CO2. Okay, a molecule we all know. All right, but carbon, again, has 4 valence electrons. I have oxygen that has 6 valence electrons. And there's 2 of them, so that's 12. Okay, so 12 and 4 is 16 valence electrons. Okay, so carbon's going to go in the center. We're going to place 1 oxygen on either side. In doing that, we have used 4 electrons for the bonds. And so that means we have 12 electrons remaining. And so 2, 4, 6, 8, 10, 12. And so that's all the electrons that I have. And so at first glance, it looks like this might be okay, except that I did not satisfy the octet, or carbon in the center only has 4 electrons around it, so it does not have a full valence shell. Okay, and so when this happens, you may remember, according to the rules, since I don't have enough electrons, what we're going to do is we're actually going to move this pair from the outside, from a lone pair, to the inside and make it a bonding pair. Okay, and since I'm short 2 pairs of electrons, right, I would need a pair here and I would need a pair here. I'm going to have to do that twice, so I am going to do it on both sides. Okay, so I'm actually going to take these electrons out. I'm going to go ahead and put an additional bond in between there, 2 double bonds. Okay, and so now I'm going to reevaluate my structure. Again, there's a little bit of back and forth that happens here. Okay, and so I see this carbon here has 8 electrons. I see that this carbon here has 8 electrons. Remember that that double line represents a double covalent bond, which is 4 electrons shared in between the carbon and the oxygen here. Okay, and the carbon and the oxygen here would share 2 pairs or 4 electrons. Okay. And then the carbon in the center also has 8 electrons. The last thing I'm going to do is just double check that I've used the right number of electrons: 2, 4, 6, 8, 10, 12, 14, and 16. So that is the Lewis structure for carbon dioxide. All right, last one then. Let's take a look at N2. And so nitrogen has 5 valence electrons, and there are 2 nitrogens. So this is 10 valence electrons we have. If I form 1 bond in between nitrogen and nitrogen, okay, I would need, so that's 2, and then I would need 4, 6, 8, 10. So I'm actually short, again, 2 pairs of electrons from satisfying the octet on both nitrogens, okay? So however many pairs I am short is how many additional bonds I'm going to need to form. So I'm going to go back and remove 2 pairs of electrons from nitrogen, and I'm actually going to go ahead and put those in the middle, okay? And so this is 8 electrons around this nitrogen. There are 8 electrons on this nitrogen, and I have used 2, 4, 6, 8, 10 electrons. So again, going back and verifying that I have used the correct number of electrons there. Okay, so we'll continue to practice Lewis structures again in the next couple class periods. But for now, that should give you a little bit of an introduction to reminder on valence electrons and how we are going to draw Lewis structures.